All right, so switching now back to the moon, one of the most interesting things about the moon is just its mass, really, because its mass leads to a calculation of its surface acceleration, which is always fascinating because of that then gives us the relative weight that we would have on the moon relative to our weight on the Earth. So, first of all, we need to be able to compute the mass of the moon. The way we would compute the mass of the moon is by actually measuring the acceleration that some object is experiencing. Because if we can measure the acceleration that an object experiences in lunar gravity, now this object would have to be a satellite or something to send near the moon, right? Send a satellite out near the moon, it's going to get deflected by the lunar gravity. We can measure the acceleration of the satellite, and that's related to the mass of the moon and the distance that you are from the moon, that the satellite is from the moon. We can turn this equation around and then solve for the mass m, and that turns out to then be minus a times r squared over g. All right, now, we know how far the satellite is from the moon, because we know about the satellite's orbit. So we know that distance r, and we know the universal gravitational constant, and we're measuring the acceleration. So what that means is we can combine these observations and calculate the mass of the moon without actually going there physically. We just have to have an object that we can observe as it moves with the effect of lunar gravity. And what we use from these observations is 7.4 times 10 to the 25 grams. 10 to the 25 grams. Now, until we had satellites that actually moved through the lunar gravity, there was actually no way to do this. Because you really can't estimate the mass of the moon that well just from the tidal effects, because it's difficult to calculate that force. You can kind of get in the ballpark, but the number as accurate as this, or more accurate, required us to send a spacecraft there, because the moon has no moon of its own. The moon has no satellite orbiting it, which we could observe and use to deduce the mass of the moon. It's a little different when we move to other bodies that have moons. Like, for example, Jupiter has many, many satellites. Has many, as we call them, Galilean satellites that we can observe from the Earth. So when we look at Jupiter, we can see little points of light moving around Jupiter. Those are its own satellites. Those bodies are actually participating in the gravitational effect of Jupiter. And by observing the acceleration of the moons of Jupiter using a telescope, we can actually calculate Jupiter's mass. But since the moon doesn't have any natural satellites, we have to actually send a spacecraft there. So we get that mass, around 7 times 10 to the 25 grams. And of course, the radius of the moon is easy to calculate because we know its distance. We can just measure its angular size and get its radius very easily. It's basically a spherical body, so we use the spherical formula for the volume and get a volume of about 2.1 times 10 to the 25 cubic centimeters. Well, just as we did for the Earth, we combine the mass with the volume to calculate the average density of the moon. Divide 7.4 times 10 to the 25 grams by 2.1 times 10 to the 25 centimeters, and the big numbers cancel out, and we get about 3.5 grams per cubic centimeter. Well, the first thing you notice about this is it's nothing like the average density of the Earth, which is closer to 6 grams per cubic centimeter, right? So just right here, just with this one number, we know that the moon's interior structure and probably its composition are quite different from the Earth's. This number actually is quite similar to the density of surface rocks on the Earth. So one could reasonably surmise that the moon is pretty much made of material that's kind of similar to surface rocks on the Earth. That turns out to basically be true. Not much iron on the moon or inside the moon, not much of an iron core. Because if the moon did have a substantial iron core like the Earth, that would push its density up to the Earth-like range of 6 grams per cubic centimeter. We don't see that high density, so there can't be much iron, and therefore not a dense iron core. Again, just some characteristic numbers. Density of water is around 1 gram per cubic centimeter. Surface rocks are in this range. And so, again, we know that the moon actually must have roughly a surface rock type of composition. Okay, so surface gravity of the moon. Well, what we're talking about is the acceleration, again, acceleration experienced by a body near the moon. And we've already talked about this anyway. The acceleration is going to be related to the mass of the moon and to the distance you are from the moon squared. Now, if we're on the surface of the moon, this r simply becomes the radius of the moon. It's sitting right on the moon. So this formula would actually give us the acceleration that would be experienced if you dropped an object near the moon, right? If you have an object like my laser pointer here, it's moving with 0 velocity right now, right? And then every second it adds velocity to its initial velocity is 0, but a second later it's moving with some additional velocity, and then it keeps accelerating, right? So that acceleration of the surface of the Earth is 9.8 meters per second. So every second that my laser pointer falls, we have an addition of 9.8 meters per second to its speed, right? And so now we're interested in what is that number on the moon? What's the rate of acceleration on the moon? Well, if we do the math by taking the moon's mass and its radius, we do this calculation, we get 1.7 meters per second squared, which is a heck of a lot less than the surface acceleration on the Earth, 9.8 meters per second squared. This also actually corresponds to a calculation of your weight, essentially, because remember that the way we compute a weight type force is going to be a mass times acceleration. So on the surface of the moon, the force that you're actually exerting on the moon, and that's what we actually mean by weight, is the force that your body's exerting on the Earth, on the moon, by virtue of gravitational force. That's what the weight is. It's actually a force. It's going to be mass times acceleration. So if we have a spring scale and we carry our trusty spring scale to the moon, the spring in the spring scale works exactly the same way as it does on the Earth, because the spring doesn't care about gravity. It's just a mechanical device. So we can take our spring scale to the moon and we can actually measure this force, because that's what spring scales do. When you step on a spring scale, your gravitational force is squishing the spring. And the spring, as the spring compresses, it pushes back harder and harder. So eventually the spring stops compressing, and the spring is connected to a needle, and the needle reads your weight, right? So spring scales don't actually measure your mass, they measure the force of gravity that you're exerting. So that's going to be proportional to this acceleration now. So what that means is that if we look at the ratio between these two factors, the ratio is about 1 to 6. That's the same ratio that's going to reflect your weight on the moon versus your weight on the Earth. It's a 1 to 6 ratio. So objects on the moon are only going to weigh a sixth of what they weigh on the surface of the Earth. Now, this led to special training requirements for astronauts who are going to be walking around on the moon, especially those who are going to be scooping for those giant lunar cats. That's dangerous business. You don't want to lose your footing for obvious reasons. Now, the thing is that the actual strength of the body is the same, because that's a chemical thing. You know, you're just as strong on the moon as you would be on the Earth, so your leg muscles have the same strength. So you can push off just as hard with your legs on the moon as you can on the Earth. The 180-pound astronaut on Earth is only going to weigh, 30 pounds on the moon. So the difference is that your leg strength is the same, but you weigh a lot less, only 1/6 as much. So when you kick off with your maximum force, like you're trying to do a high jump or something, you're clearly going to go a heck of a lot farther because you're being launched. You're actually pushing off with a much stronger acceleration because your mass is, the force is actually so much lower, force of gravity. So moon jumps are always going to be much longer than Earth jumps. But the catch is that your mass is still the same. Mass is not the same as the weight. The weight is the force of gravity exerted on the body is the weight, but the mass is just the amount of matter in your body. So the mass is still the same, and mass is connected with inertia. So once you start moving with a certain speed, you have just as much inertia on the moon as you do on the Earth. So the relationship between inertia and weight gets thrown off, and this becomes kind of counterintuitive and can lead to what we call cracked faceplate syndrome, which is bad, very, very bad on the moon. So we had to train astronauts to be able to jump around. This is a shot over at the Air and Space Museum in DC. This is the Saturn V rocket, the most successful rocket series in history. The only rocket series in history never to suffer a single failure. Every test and launch was successful with the Saturn V series of rockets. And this is the Soviet version, the Proton thing there. This was the mid-1960s during the space race, because the USSR was in a race to get to the moon, because that was the big national prestige thing to do in those days, was go to the moon. So we had these two rocket series, and the Proton actually was not as successful. as the Saturn V series and actually suffered a number of embarrassing complete blow-ups on launch. So, so the good old US of A actually did get there first. This is a mock-up with not live astronauts there. This is also at the Air and Space Museum. And this is a lunar module, which actually was one of the training lunar modules. It's not a mock-up, it's a real lunar module that was used for, was slated to be used for training purposes, but the training sequence was so successful they actually never had to use this one, so they donated it to the Smithsonian. But my real reason for pointing this out is that there's a plaque. You see this informational plaque right here. And if you look closely at this thing, it has an amazing thing on it that they don't point out at all here, but of course I noticed this thing. Now this is of course supposed to land on the moon. This is a lunar module with a big rocket thruster there, which is the retro thruster that allowed it to land on the moon. There's no parachutes. They did have a backup parachute, but they never used it. Why did they never use the backup parachute? No atmosphere. They can deploy the parachute all they want. It's nothing going to happen. They have to land with a retro on the moon. So there's a big retro rocket there that actually allowed us to land. And when the astronauts took off again, this lower part stayed behind, and the upper part took off. This is another little ascent engine in there. All right, now think about it. You've got the force of gravity exerted on the object. Your thrusters are going to create a certain amount of thrust. The thrust of the rockets is measured in pounds, and it's a chemical reaction, so it's the same anywhere in the universe. You can take the same thruster on the Earth, on the moon. It'll create the same amount of rated thrust because it's a chemical reaction. Now look at the contrast here. If you look at the total thrust of the descent engine. Now the descent engine is the one that are coming down. That's the biggest motor, the one on the bottom, right? The descent engine's thrust is about 10,000 pounds maximum. But if you actually look at the weight of the crew and propellant and everything else, it's about 32,000 pounds. So I just found it fascinating. You see this number here, 32,000 pounds is the weight of the spacecraft and everybody in it and propellant. And the main descent engine only produced 10,000 pounds of thrust. So I mean, it looks dangerous. I mean, of course, the answer is the weight that they're talking about there is the Earth weight, right? When they say weight, they mean, you know, our conventional notion of weight is weight on the Earth, right? So the spacecraft with the crew and propellants weighed about 32,000 pounds, but that was on the Earth. So the point of this is that you could not land this craft on the Earth because the descent engine only produced 10,000 pounds of thrust. Only, you know, around a third of what would have been required just to overwhelm the gravitational force. So this thing would have actually just accelerated right down and gone flat on the Earth if it tried to land on the Earth. But on the moon, big difference, because these weights all get reduced by a factor of 6, right? That factor of 6 I was just talking about. So on the moon, the 32,000 pounds actually now is only about 5,000 pounds. But the rocket still has 10,000 pounds of thrust because the rocket's chemical reaction is going to do the same thing. So there's, you know, the explanation, if you will. This did work, you know, it actually did work many times on the moon because the weight was so much lower. I actually just realized there's conspiracy theories still, I think, going around that we never really got to the moon. You know, I'm not even sure why they think we never got to the moon, but they just think we never got to the moon. Now this would really be great. I mean, maybe somebody's already picked up on this, but I can imagine somebody blogging. Yeah, I went to the Air and Space Museum and I found another piece of evidence that supports my theory. Look at that. It couldn't have worked. 32,000 pounds and only 10,000 pounds of thrust. Of course, they would be, you know, missing the point I just made if they did say that. But anyway, okay, I guess I'll just end that here and we'll finish up the chapter on Thursday.